Hello everyone, and we're back with our discussion on projectile motion. We are discussing angular projection. In the last video, we began with our introduction on angular projection. And in this video specifically, we'll be discussing the path of projectile. So let's see, what do you mean by the path of projectile? Now, the reason I want to discuss the path of the projectile is because I have been drawing the motion of the projectile in this way. Now, who told us that the path of the projectile in angular motion will take this shape? We do not know yet why exactly it is this shape that we are drawing for the projectile motion in angular projection. So, what I want to do is try to find out the answer to this using maths. Now, specifically, I am going to use kinematical equations, and I am going to use this equation to prove to you that this should be the path of the projectile. Now, we all know this kinematical equation. Let me recap what are these quantities. In this kinematical equation, this is the final displacement, this is the initial displacement, this is the initial velocity, this is the time taken for the motion, A is the acceleration, and T is again the time taken. Now, using this equation of motion, I will find for you the path of projectile. Now, the way to do that is to first analyze the motion along the x direction, find an equation for that, then analyze the motion along the y direction, find an equation for that, and then use both those equations, combine them, and what you get is the path of a projectile. So, let's begin. I'm going to say that when I project an object through angular projection, I'm going to take a look at some general random point in the motion. So, at some random point P during its motion, I say that this object has covered some horizontal distance, which I will call as x, and it has of course covered some vertical distance, which I will call as y. So, at some random point in the motion, we will say that the general horizontal distance is x and the general vertical distance is y. And what I want to do is find out an equation for this x and find out an equation for this y. So, let's see how we're going to do that. I'm going to need these values and the understanding of this diagram, and we'll also remember that initially this object had a velocity u, which we have resolved into two, u sin theta and u cos theta, like we did in the previous video. So, this is the amount of information we need. And remember that initially the x direction velocity is u cos theta, y direction velocity is u sin theta initially, and after some time these values will change, that is u sin theta will change, but u cos theta remains constant because there is no force acting along the x direction. This is something I have made clear in the previous module. So, I am going to need all this information, so let me capture that and place it on the side. Now, let me use this information to find the path of projectile. Like I said, I am first going to analyze the motion along the x direction. So, if I try to analyze the motion along the x direction, let me see what I know. Now, I know that I am going to use the kinematical equation which I had written previously, but this time I am going to use it only for the x direction. So, if I write down the equation only for the x direction, this is what it looks like. I am going to use the equation x is equal to x naught plus uxt plus half axt square. Now, pay careful attention. X is the final displacement of the particle, x naught is the initial displacement, ux is the initial velocity, t is the time taken for the motion, and ax is the acceleration. So, let's see if we can answer what the values of these quantities should be. If you take a look at the diagram, we are only looking at the horizontal direction. So, remember, we are only analyzing the x direction. So, let me analyze only the x direction. In the x direction, if I ask what is the final displacement, the final displacement is x. Am I right? At this point, the displacement of the object is x in the horizontal direction. What was its initial displacement? Initially, it was at the origin. So, the initial displacement was 0. So, I can say x naught is 0 and x, which is the final displacement, is nothing but x itself. Also, remember that the initial velocity along the x direction is u cos theta. So, I say ux is equal to u cos theta, and we also know that there is no force acting along this direction and therefore Ax is 0. Finally, I say that let t be the time taken for the object to finish this complete motion from O to this point P, and therefore I say just t is equal to t. Now once I do that, I'm going to put all these values into this equation, and what I get is x is equal to 0 plus u cos theta t plus half 0 into t square, which gives me x is equal to u cos theta t. From this, I get a final value for t, that is t is equal to x upon u cos theta. I'm going to need this equation, so I'm going to save it. This is my first equation. Now I'm going to apply the same kinematical equation to the vertical direction. If I write down the equation that I'm going to need, it's the same equation as this one, but I'm going to write this equation specifically customized for the y direction. So let's take a look at the equation along the y direction. The equation will be nothing but y is equal to y naught plus uyt plus half ayt square. And again, I'm going to apply the same analysis to the y direction. Finally, if you see at the point of observation, the total displacement is y itself. And what is the initial displacement along the vertical direction? Again, it is 0. Remember again, now I am talking only about the vertical direction. So final displacement along vertical direction is y. Initial displacement along vertical direction is 0 because object starts from origin. So I say y naught is equal to 0. Let's also see that the initial velocity along the y direction is u sine theta. So I say that uy is nothing but u sine theta. What is ay? Now this is where it is important to take notice. Ay is the acceleration which the object is feeling along the y direction. Now along the y direction, the only force acting on the object is gravity. Now the object is moving upwards, whereas gravity is pulling the object downwards, and therefore ay is nothing but the acceleration due to gravity, but it will be a minus g, and it's minus because object's velocity is decreasing. As the object is going up, its velocity is decreasing. So because the velocity is decreasing with time, the acceleration is negative. So ay is equal to minus g. And finally, I know that t is equal to t because the same time it takes for the object to go from O along the horizontal direction is the same time that the object takes to go from down to up to point P. So finally, I'm going to put these values in equation 2, and what I get is this. I get y is equal to 0 plus u sine theta t plus half into minus g t square. Now finally, what I'm going to do is I'm going to put the value of this t into this equation from equation 1. So you can see t is equal to x upon u cos theta. I'm going to take those values and put it here. I'm going to say y is equal to 0 plus u sine theta, and instead of this t, I'm going to take this from here and I'm going to put it over here. So let's write down what that would be. Y is equal to u sine theta, and take this value of the t and put it here. And I'm going to get minus half g, and again for this t also I will take another value from here and square it because it's t square. And when I evaluate this equation, what I will get is the final answer, that is y is equal to x tan theta minus bracket half g upon u square cos square theta the whole x square. Now this is the final equation that I need. See again what I did. I analyzed the motion along the x direction, found the value of t because I want to eliminate t finally. So I found the value of t in terms of x, initial velocity and theta, and I used that in my equational analysis for the y direction, and I got this final equation, that is y in terms of x with known quantities. Now this equation itself is not something that you will always need. Very rarely you will get an equation like this that you need to remember. Why I need this equation is because now it's very clear that this equation is an equation of the type y is equal to ax plus bx square. And remember, if you already know that any equation that looks like this, let's take a look. Does this equation match this equation? Yes, it does. Tan theta is like the a, you have the x, minus of this whole bracket is the b, and you have x square. So this equation can be written in this form, and any equation of this form always represents a parabola. And it is this equation which gives us the right to draw the equation of motion in angular projection in the way that we do. And this proves then that the equation of motion in angular projection is that of a parabola, and hence the path of a projectile projected at some angle with the horizontal direction from the ground is a parabolic path. So this completes my proof that the path that an object takes when it is angularly projected is going to be parabolic. I hope you understood now why we draw an angular projectile motion in this way. So I hope you liked the video where we describe the path of a projectile. If you like our videos, please subscribe to our channel, click below. And if you'd like to buy your very own target book, you can click on this link and get one for yourself. Stay tuned for more videos and keep watching.